especially the digital electronics. So transistor, if you talk about the transistor, and then transistor is the part of electronics. If you classify this electronics, then we have analog electronics, and then there is a digital electronics. The whole story was started 1947 AD when our country got freedom. So digital part was started right back. That is a binary number system. Binary number system. This was discussed in long back. It is 1705. Long back, it is 1705. Then there is 1850. That is George Boole, who gives the Boolean algebra. Then it is 1886, switches on the basis of electrical switches. That is, gives the concept of logics. And then transistorized computer. Transistorized computer. And this was started in 1953 by Tom Kelbe and IC circuit in 1958 and 1959. In 8 it was using germanium. In 59 it was silicon. So silicon was developed by Kilbe, and this was Hoemni. So these are the few timeline of the digital electronics. Now, if you comes to this part, analog. So in 1947, when there was a discussion of diode. Diode means this is P-type and N-type semiconductor, that you have circuit symbols simple like this. And the diode equation is I is equal to I0 e raised to the power EV upon NKT. This is again expressed as I0 e raised to the power V upon NVT, where VT is noise voltage, it is KT upon E. And you see the K is Boltzmann constant, 1.38 into 10 to the power minus 23, and this temperature, and divided by the electronic charge, 1.6 into 10 to the power minus 19 Coulomb. So this is T upon 1100,650. And if you are placing 300 Kelvin at a room temperature, divide by 11,650. So you'll get, this is 26 into 10 to the power minus 3 volt. That is the famous 26 millivolt. This is VT. and it is termed as what is VT? VT is noise voltage. Noise voltage, which is the big problem, or you can say biggest problem in digital electronics. We will study as a noise margin. Okay. So this one is the VT, that is 5026. Now
सबसे बड़ी कोड है जहाँ फाइनल डिसीजंस लिए जाते हैं। मतलब जो सुप्रीम कोर्ट ने कह दिया। सबसे छोटी वाली कोड कौन सा है? सबसे छोटी कोड।
Please mute your audio.
पहले डिस्ट्रिक्ट कोर्ट में अगर उन लोगों को डिस्ट्रिक्ट कोर्ट का फैसला अच्छा नहीं लगा तो फिर वो जाते हैं हाई कोर्ट में। फिर अगर हाई कोर्ट का फैसला
Soumya, you please mute your audio.
तो मानना ही पड़ेगा फाइनल।
Soumya, mute your audio. Now the second point first is we have to noise voltage, which is 26 millivolt, and the second point is typical value. Typical diode equation, that is
तो इजी चीज है, वो तो मैं भी बना लूं कट करके। अरे मैगी तो सब लोग बना लेते हैं। अरे बनवा तो
typical value of this current I is equal to I0 e raised to the power V n Vt. This V is sometimes say V gamma. This V gamma is cut in voltage. You have the standard value of this cut in voltage. Now you take the typical values, that is I is the current, and say the current is of the order of 10 to the power minus 3 ampere. That is 1 milliampere. I0 is saturation current. We can take the value that is 10 to the power minus 9 ampere. And this is E. E, we have to find out this V gamma. N is 2 of the, say, germanium material. And this one is VT. VT is just, we have calculated 26 millivolt. 26 millivolt. So by this typical value, what we have to do, we have to solve it. So this is 10 to the minus 3, and here it is 10 to the power minus 9. So you will get, this is 10 to the power 6. And this is E to the power V upon 52 millivolt. Taking log of both the side, exponential log. So what we will find? This is 10 to the power 6. So this 10 to the power 6 is 2.303 into 6 is equal to log E base E is 1. So this is V gamma, which is divided by 52 millivolt. This is divided by 52 millivolt. So from this, we have V gamma is equal to, this is 2.303 into 6 into 52 milli 10 to the power minus 6 volt. And this value is 0.73 volt. So V gamma is 0.7 volt. This is theoretical value. This is theoretical value, and experimental value is 0.75 volt. This is experimental value. This is V gamma. Now, why this one is important? This 0.73 and 0.75, whatever it may be, we have this kind of the VI characteristics, say the V, and this is I. And you can say it is diode characteristic. So this is something like this, and this value is V gamma V gamma is, this is 0.73 volt, 0.73 volt theoretically, yeah, 0.7 volt is 0.75 is experimentally. So why this value, either 0.7 or sometime you can change this value is, this value V gamma, you can change this value is less than 0.8 and greater than 0.6, greater than 0.6. This value is ranging. So what is the importance of this value? There are two questions. The first question is, why it is 0.73? Why it is 0.73? So the answer of 0.73 is here by taking the diode equation. This one is the diode equation, and from this diode equation we'll got this one is. This one is a big problem with the students, that once you ask कि ये डायोड कैरेक्टरिस्टिक में कट इन वोल्टेज 0.73 कहाँ से आ गया, तो स्टूडेंट्स बिल्कुल एकदम अवाक कि कहाँ से आ गया, ये तो हमने कभी समझा ही नहीं कि कहाँ से आ गया। तो ये चीज बहुत जानना जरूरी है कि कट इन वोल्टेज का जो वैल्यू है वो डायोड इक्वेशन से आता है। डायोड इक्वेशन यहाँ पर आपके सामने हमने लिख करके इसको निकाल दिया। इसमें दूसरा इंपॉर्टेंट कि नॉइज वोल्टेज क्या है, 26 मिली वोल्ट, ये कहां से आता है वो भी चीज यहां पर क्लियर हो गया। तो दो न्यूमेरिकल वैल्यू ये एनालॉग से मिल गया, और ये दो न्यूमेरिकल वैल्यू जो एनालॉग से मिलता है, दीज टू आर वेरी इंपॉर्टेंट फॉर आवर डिजिटल इलेक्ट्रॉनिक्स, क्योंकि इसका बहुत ज्यादा इंपॉर्टेंस है आगे की तरफ। सो लेट अस सी द नेक्स्ट पार्ट। सो this digital electronics that is based on binary system,
सर पता नहीं क्या पढ़ा रहे हैं,
binary number system।
नहीं बोलो।
मैं डिजिटल इलेक्ट्रॉनिक्स का बेसिक कॉन्सेप्ट पढ़ा रहा हूँ। हेलो,
माइक खुला है क्या?
मैं बेसिक इलेक्ट्रॉनिक्स पढ़ा रहा हूँ, डिजिटल बेसिक इलेक्ट्रॉनिक्स, ठीक है। अब बाइनरी नंबर सिस्टम we have 0 and 1 state. 0 and 1 state. 0 state is represented at cutoff, or 1 state is represented at saturation. ये saturation है। कहां पर ये saturation cutoff आता है? It is switching action. It is switching action. किसका switching action? किसकी switching action आता है? ट्रांजिस्टर का। So you take the characteristic common emitter configuration, the output characteristic, common emitter configuration के output characteristic. What is the output characteristic? You see, this one is the output characteristic. Here it is, this is VCE, and this value is IC. This value is IC. So common emitter output characteristic में there is a curve at which IB is equal to 0. That is base current. And here it is IB. This is not equal to 0. ठीक है? तो output में we can plot this output characteristic as a load line. As a load line. We are interested here to discuss about the DC load line, not AC load line. So this is DC load line. This part, the below from this portion, it is known as cutoff region, cutoff of the transistor, and this cutoff transistor is identified as 0 with respect to Q point. And this one is saturation region, and this saturation region is 1. This saturation region is 1. So this Q point moves to the cutoff transistor, get it off state. This is off state, and if this Q point is moving to saturation, then it is on state. So off state is 0 and on state is 1. So this binary number concept is realized with the respect to the transistor. Now this on step and off step means switching action. If we discuss about the switching action of the transistor, so how can we identify switching action? Suppose this is the time and here it is the current, IC, current. So the switching action graph can be represented as in this way. Here it is the IC max. This is IC max. And this IC max here, this is 90%. This is 90% of the maximum current. And this is 10%. This is 10% in terms of milliampere. 10%. Here it is 0. It is 10%. So we have to find out the time. You see this value from 0 to 10. 0 to 10% of the current is 0 to 10% of current is represented as delay time. हेलो, हाँ नमस्कार सर, अभी क्लास में है सर. नहीं, डिपार्टमेंट में नहीं है, घर पे क्लास ले रहे हैं सर. ठीक. This is 0 to 90%. It is known as rise time. This is rise time and it is 40 nanosecond. Sorry, this is second. This is nanosecond. So this delay time and rise time, that is TD plus TR, rise. How much it is? 10 nanosecond plus 40 nanosecond. So it is 50 nanosecond. 50 nanosecond. So what we find here, from 0 to on state. 0 to on state, so T on is 50 nanosecond. T on is 50 nanosecond. This one is. Now, from this point, this up to 90, this is T storage time. This is storage time from 90% to 10%. This is this TS and this is T fall. This is T fall and this T fall is this is 40 nanosecond and this is 30 nanosecond. So it is 70 nanosecond. What I want to say, this T off from maximum to 0 is 70 nanosecond. 70 nanosecond. So one thing is clear. You have to rise time is 50 nanosecond and fall time is 70 nanosecond. So what you find from 0 to maximum? So you see from here, from this state, cutoff state to saturation state is the rise, and this take the 50 nanosecond. And from saturation se cutoff, from this saturation se cutoff, you are getting the 70 nanosecond. This is the switching time. So what is the difference? How it makes the transistor volatile? Now the signal is if you say the pulse, then there is a rise time and there is a fall time. The rise time and fall time. Now let us take one example. The simple example is, suppose this is the medium of communication. Medium of communication, say fiber. and you are giving a pulse. Here it is pulse in input. This is your input, and the output pulse is received. What are the various conditions of the output pulse? The output pulse may be as identical. This is T. Here it is T1. The second is something like this. The third is this. This one is T1. This one is T2. This is T3. And this is T4. What this one is, this T1 is same as T. Same as T means the input time. Here T2 is greater than T. T3 is greater than T. T4 is greater than T. T4 is greater than T. So now the question is which will be the output pulse? Which will be the output pulse amongst the four, A, B, C, D? This was the question that I have put before, and the answer now, without getting any delay, I like to give the answer. So the answer is D. Answer is D. What is the, why it is D? Why it is D? Before going to answer why it is D, I have to see why it is not A, B, C. So let us see one by one. In case 1, A, this T1 is equal to T2, means the output is exact replica of input. So if there is a communication and the output will never be replica of input, there is some sort of change. Now this T2 time of the width will increase definitely, but the amplitude will not be remain same. Amplitude, this part, this amplitude will not remain same throughout the time because of attenuation loss. Now here the T3 is greater, that delay is there, but here the amplitude is increasing. Amplitude in increasing means this fall amplitude and rises. This is rise age and here it is fall age. You can say this age is rise age and this is fall age. So the rise age is less than fall age. The fall age is having. It is not possible because if the amplitude of fall is higher, it means the medium gives the energy, which is not possible because media is always attenuative. Now this is why it is now the fourth one is, if all three are not possible, then definitely 4 will be there. Now the 4 will be there. The reason is, the first reason is T4 is greater than T due to delay. So it is latency. Sometimes it is also called as latency. Latency in communication of data. This is a very common feature in transmission of the data. आप मोबाइल से जब कुछ भेजते हैं, एक जगह से दूसरे तक डेटा भेजते हैं, डेटा कैसे हो सकता है? वॉइस का डेटा हो सकता है, टेक्स्ट मैसेज का डेटा हो सकता है, वीडियो का डेटा हो सकता है, कोई भी डेटा हो सकता है. तो जब डेटा भेजते हैं तो उसमें लेटेंसी आता है, देर होता है. The second point is, you see, this is the rise amplitude, here it is fall amplitude. So fall amplitude is less than rise amplitude. It means the output part of the energy is less and it is due to attenuation. So media is lossy and lossy media is attenuating. And that's why this fourth answer is correct. Now, if you see if you see the ideal pulse, this is the ideal pulse. This is the ideal pulse. But what is the actual pulse? Is it ideal? Actual pulse is something like this. This is the actual pulse, because you have, this one is rise time, this is T on, and here it is T off. This is T off. So it may be some change in the gradient, this angle, but the time is there. The time is there. So in typical cases, we have just discussed, it is 50 nanosecond, and here it is 70 nanosecond. 70 means what we say कि fall time is more than rise time. तो कोई भी pulse है, pulse में rise time जो है वो 50 nanosecond का है, और fall time जो है 70 nanosecond का है. तो 70 nanosecond के वजह से इसका जो gradient होगा, you see this gradient, this slope is greater. This is a steeper. This is the steeper, this sharp rise, because it is 50 nanosecond. 70 nanosecond, it is the fall, which will be discussed in sequential circuit, which make the more impact on this one is. So these are the some digital part. And if you talk about the time, how it is delay time, how it is fall time is concerned with this case. So we will very easily discuss this whole concept with the taking example, because this T delay is T high to low plus T low to high, and whole divided by 2. Whole divided by 2. So how to define high to low and low to high? You see, if you take the pulse, one pulse, and this one is suppose input pulse, input something like this, input pulse, and then there is output pulse. How this output pulse is there? This is the output pulse. So this time is T. This is low, this is high, and this is low. Here it is low, high, low, low, high, low. So from high to low, this is the low to high, and this is high to low. So this point is this point is output pulse. Here it is output pulse, here it is input pulse. Why it is this kind of shape is there? It is very obvious that I have assumed that you know the action of not. Suppose this is a transistor. This is E, this is C, this is B, here it is VCC. So if you take this input, here it is VIN. So VIN is something like this, input pulse. So the output pulse is this way. Output pulse is this way. This is input, and this is the output. And you are taking NOT gate. If it is 0, then it is 1. If it is 1, then it is 0. So NOT gate truth table. How can you say 0 means this is 0? If it is 0, then output is 1. If it is 1, then output is 0. If it is 0, then output is 1. So this input pulse is here, and here it is the output pulse. So you say you take this one is time, this is t time, this is t time high to low. This is high to low. And here it is low to high. This t time, this is low and this is high. So this time is t low to high. And this is t high to low. So t high to low plus t low to high. T high to low and t low to high divided by 2 is giving the delay time. Giving the delay time in case of pulse, that pulse is creating over here. So on the basis of what we have in digital circuit, that is digital circuit, the simplest digital circuit, simplest is NOT gate. NOT gate. Just we have discussed this NOT gate as very simple circuit. Here it is V output. This is C. This is RC. Here it is RB. And this is VI in. And here it is the emitter. It is grounded. Emitter, and then it is grounded. So you take the case 1 when input is low. Case 1 when input is low. Input is low, that is this kind of pulse is there. This is low. So when input is low, then what will be the output? The output can be obtained by using Kirchhoff voltage law, KVL. What is KVL? You see, V0 is equal to VCC minus
IC RC.
RC. Okay, this is your KVL. So you are taking the value, that is VCC is 5 volt, RC is 1 kilo ohm, RB is 100 kilo ohm, and this beta is 100. This beta is 100 of this transistor. So what will be the value? And if VCC minus, what is RC? This IC is equal to beta into IB. And this beta into IB, V input upon RB. This is the IB base current. Here it is the IC collector current. So this RB is 100 kilo. You see 100 kilo ohm, and this value is, so what will be the IC? You see IC is equal to 100 into VC 0 upon 100 kilo ohm. So this value is 0. IC is 0. So VCC minus IC, that is 0 into RC, this is VCC. So V0 is VCC, that is 5 volt, and it is high. It is high. So high means this one is something like this. This is 1. Case 2. Case 2 when input is high. Input is high, that is again KVL. The V0 is equal to VCC, IC, RC. So VCC, and now in this case, when for high input, IC is equal to beta VI upon RB. So this is 100 multiply 5 volt divided by 100 kilo ohm. So this 100 and 100 cancel. This 100 and 100 cancel. So it is 5 milliampere. This is IC. IC is 5 milliampere. This kilo is here and that will make. So VCC, you are taking this VCC 5 volt as it is given here. IC is 5 milliampere and RC, this RC value is 1 kilo ohm. This is 1 kilo ohm. This is 1 kilo ohm. So this kilo and milli cancel. This 5 volt minus 5 into 1. That is 5 minus 5. That is 0. So V0 is 0. V0 is 0 means low. Low. So if input is high, output is low, and this is low. And again 1. So this is the very simple. This is the very simple NOT gate. Now, this simple NOT gate can be explained with the block diagram. You see, this one is the block diagram.